Hi, I'm Ben-Yaakov. This presentation is entitled Stored Energy in Nonlinear Inductors, an Answer to Riddle. This is a riddle that I have posted earlier. I'm giving here an answer and also expanding a little bit with some further explanation. There is a relevant reference, which is a paper of ours. Here is the link, and I'm going also to put the link at the description section of the YouTube video that you are now watching. So what was the riddle, or what was the question? Consider an inductor which is built around a ferrite core with or without a gap. Now without a gap, it'll look something like that, the BH curve of the total inductor. But with the gap, the BH curve is of course shaped, and we have it with a lower permeability. Permeability is the local derivative, okay? So here we have one permeability, and here there is another, but the permeability is changing with H, which is also the current, because the slope here are of course changing. So as I move with the current from 0 to say I sub 1, I'm moving with H from 0 to H sub 1, and during that time the permeability is changing, and therefore the inductance, which is a function of the permeability, will start at a given value and then start dropping. This is very, very typical to just about any practical inductor. So the question is now the following. Suppose I reached I sub 1. How can I calculate the energy stored in the inductor, considering the fact that of course the inductance is changing along the change in the current? So this was the question. So let me start off with some general remarks about energy in inductors. Now we know that the expression for the energy stored in an inductor is Li squared over 2. L is defined as N phi over I. But all this, of course, is for a linear inductor. That is, that L is independent of the current. Now in the case of a real practical inductor, which is built around the ferrite core, which has a nonlinear BH curve, of course the story is different. So I'm showing here an inductor with a gap, air gap, and here is an inductor which could be without an air gap. Now the inductance of a body like this is N squared AE, which is the cross-section area of the core, here it is, or here, and mu 0, which is like in air or vacuum, and the relative permeability, which is a function of the current. So therefore the inductance is going to be nonlinear. This is the whole point here. So let's have a look at it a little bit deeper here. I'm showing again BH of the native ferrite without a gap. This is the core itself, the material itself. And then as I put in an air gap, the permeability is going down, and typically I'm going to see a BH curve which looks like that. This is for the whole inductor, okay? Like this will be for a air gap of say 0.1 millimeter. This is a simulation for a given core. So the permeability is actually the local slope, which is of course changing, but it is important to realize that we are talking about local, differential, or small signal permeability. Okay, so this is one way to define permeability. There are other ways. I'm not going to go into it in this presentation. In the paper that I'm citing, there is a whole discussion on that. So we are talking about differential or local or small signal permeability, and consequently we're going to have a small signal or local or differential inductance. Okay? The permeability is the local derivative, which is usually, of course, approximated in practical measurement as delta over delta. And the expression, again, for the inductance is this expression, where now the permeability, we understand now it's a differential permeability, is a function of H. And H, of course, is a function of I. So we have that the inductance is a function of I. So this is actually very well known, but this is just an introduction to the fact that the inductance is changing. So now let's go to the answer of the riddle. I'm presenting here two methods to solve actually the question. So the first one is based on the inductance itself, nonlinear inductance. So I'm starting here with what is energy. Energy is power, integral of power over time, and power, electrical power is voltage times current. Now in the case of an inductor, the voltage is L di dt, okay, L is a function of I. So now I'm going to replace V by this expression. I'm getting this, and this is now dt, di dt, which sort of drops off. So I understand now that the energy of an inductor with a change in current between 0 and I sub 1, when the inductor is non-linear, is this expression. So you have to do this integral. Obviously, LD has to be expressed in some way. Could be fitted to a polynomial or some other non-linear function. And then you have to carry out this integral from 0 to I1, and this will give you the energy. Now, just to show that this makes sense, let's take the case which is normally assumed that L is constant. Well, if L is constant, then this is a constant number, so I can take it out as a matter of fact, and then I'm left with I di, which boils down to this solution, which is very well known. Of course, this is the one we talked about earlier. So this is the solution to the question. You have to do this integral. You have to know what is the differential or local or derivative inductance as a function of current, express it in a way that you can take this integral, and this will be the energy stored in this inductor. Another way, which I really like much better, but it is not very familiar to electronic engineers. It is something that physicists would sort of consider. Now, for some reasons that I'm not sure why, electronic engineers are not familiar with this, I'd say, way of thinking, okay? Well, the point is that energy per volume is this integral. This comes out actually from Maxwell equations, which I'm not going into it because it's kind of elaborate, and I'm going to try to make this intuitive. So let's take this as the basis. I'll show later on that this, of course, is compatible with all that we know, but this is another way. We're not talking about inductance. Now, inductance is not a basic parameter. It is a sort of defined parameter based on some known other parameters, as I've shown, phi or n phi over I. So going back to the roots of electrodynamics, this is the expression for energy per volume. Integral of H with a change of B for the range of B that we are talking about, when H is a function of B. Now in the linear case, so I'm going first to show that this makes sense. For the linear case, H is B over mu, and mu is linear. Okay, this is the linear case. So therefore, if you look at this integral, so the energy is the volume times B dB. I have replaced H with B over mu, and this comes out to be B squared over mu 0 mu r times the volume. And of course, you can replace B over mu by H, and this is a very familiar expression. Okay, HB over 2. This is the energy in a volume. This is per volume, and if you multiply it by the volume, this is the energy stored in this volume. Okay, now let's see if this thing makes sense and is compatible with what we are used to. Okay, so energy from here, and now I'm replacing B by H times mu, is the energy is the volume times this mu H squared, so this is B times H over 2. Now H is Ni over Le. Volume of the body we are talking about, where the energy is the cross-section times the magnetic path length. So this is the volume. And when I replace the volume in here is what I'm getting. So I'm getting mu r, n squared, AE, cross-section of the core, LE. And lo and behold, this is the expression for the inductance of an inductor built around the core. So we are getting Li squared over 2. So I've shown that this and this are compatible, and exactly the same, of course, for the linear inductor. Now, what happens if the inductor is not linear, which is the question that I've posed? In this case, mu sub r is not linear, and of course, this is not the expression. Now, very, very interesting is the fact that this integral h dB, is this area here. This is this area. Or in the case of a core with a gap, this will be the area. Okay? So if you calculate this area, if you know the BH curve, which you have to know anyhow to get the permeability as a function of H or I. So if you know this curve, you just have to calculate this area up to this current, and then this will be the energy. So this area is energy per volume. So if you multiply this by the volume, this is the energy you get in the inductor. So in this case, this is the energy that I'm getting into inductor. Now from here we can understand now what is the benefit of adding a gap. If you have an inductor built on a ferrite without a gap, the amount of energy you can store is very small. For this current or this H, this is the energy you can get, you can store, because very quickly you go into saturation. So in the case of the core with the gap, we see a much larger amount of energy stored actually going into saturation. So once you know this energy by calculating this area here or this area here, you can do it, of course, by expressing the BH curve or fitting it to an equation and then doing a numerical integration. This is the area here or the area here. And once you do this, you can define a energy-related inductance. This is sort of an ad hoc definition, and you can define it by the formal equation for energy in an inductor, from which you can see that this energy-related inductor, of course, is a function of this expression, and it'll change, of course, with the current. So again, the important point here is that you need a gap in order to avoid saturation, because with saturation, first of all, the inductance, of course, is becoming very small, because the local derivative here is small, and therefore the inductance is small. But the point is, as far as energy storage is concerned, that you increase H, you increase the current, and the amount of added energy is very, very small. So this is not very useful for storing energy, and this is why normally you like to get a core with an air gap. Now, energy storage is not the purpose per se, but if you have a converter, say, and you need an inductor, and you need that this inductor will carry a certain current, this means that the inductor has to store energy, because you have an inductance and then you have current. So even though in many applications really you are not looking for energy storage, what is determining the ability of the inductor to function is its ability to store energy, because when you pass current through it, you actually store the energy. So if you have a buck converter with the current through the inductor, you actually store energy in the inductor. So here is a demonstration of the behavior of the different inductances that we talked about. We talked about the differential inductance, and we talked about the energy-related inductance. Now the differential inductance is the local derivative, while the energy related has to be calculated in a more complex way, depending on this area, of course, as I've said, and from that we can get the energy related inductance. And what we see is that the inductance, the derivative or local or differential or small signal inductance in this particular core is going down pretty much. But you cannot use these values at each point to calculate the energy stored in it. The actual inductance you have to take into account is this inductance based on the energy stored. As I've said, you have to get the value of this inductance, and then you can use it as Li squared over 2. And here is another view of this issue. We see here the current going up, and here is the energy stored in the inductor. The only one which is correct is this one. Okay? This is the actual. Now, if you calculate the energy by LDI squared over 2, which is incorrect, of course, because you should not take this. But if you do that, you get a much smaller number. So you cannot use this inductance for calculating the energy, say, at this point. This is a much higher inductance, because as you move to higher current, indeed, the amount of added energy is small. But you already accumulated energy. It didn't go anywhere. This magnetic energy is stored in the core, and you are adding to it a little bit, but then if you'll go back to zero, you'll get all the energy again. I mean, neglecting, of course, losses, conduction losses, etc. So again, we have to distinguish between the differential inductance, which is important for finding what is the differential behavior of an inductor for a small signal, or some delta I, and the energy stored in the inductor, and then you have to take into account, of course, the whole BH curve and how you reach the given current, say 1 amp. Now in this paper, nonlinear inductance measurement using an energy storage approach, they are proposing a method to actually measure this energy-related inductance. This is energy-related inductance because it is a function of the current and the operating point, in fact. So the suggestion is to form a resonance circuit fed by a current source, because if it's a voltage source, then it's imposing a voltage and it doesn't operate as a resonance. So if you want it to operate as a resonance, the impedance has to be high, or is to be a current source, but it doesn't have to be a current source. It could be a voltage source with a resistor in series, which is fine. And then you're going to have here a circulating current here. This current here would be much lower, of course. And of course, you have now energy throughout the cycle, actually moving from the inductor to the capacitor, back and forth. And of course, at the maximum point of the current, at the maximum point of the voltage, you have this equation. And then you can define an inductor here. This is the energy-related inductor to represent the inductance at this point, and then get this value by actually taking this over this, which is this expression here. And here is an example of one of the results that they got using this measurement setup for a given inductor, of course, and this is a ferrite-based inductor. And as you can see, it's really behaving as we would expect. At the very beginning, we have sort of a linear inductance. And then as we approach the saturation region and the curvature is, of course, increasing, then the energy-related inductance is going down, okay? So in order to get the energy stored in the inductor at, say, 10 amp, this is the value of the inductance that you have to take into account rather than this inductance at low current. So this is the behavior of the inductor that they have tested. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.